Hi everyone. In this lecture, we're going to take a closer look at equilibrium solutions, and we're going to come up with a way of classifying the types of behavior that we expect around them. So in particular, we're going to define sinks, sources, and nodes, and discuss the stability property of each of those. And then we'll come up with a way called linearization that we can use to classify equilibria. So just to give you a working mental picture of what is a stable equilibrium versus an unstable equilibrium, suppose that you had two clocks and one of them was hanging straight down and the other one was in a sort of magical position with the pendulum exactly 180 degrees up, rotated up compared to hanging straight down. Okay, I didn't say that very well, but you imagine you take the pendulum and you place it perfectly stacked above, say, the hinge, so that there's no reason why it would go left instead of right, and in that way, it's not moving. So both of these positions are like equilibria positions for a pendulum. Which would you call stable, and which would you call unstable? Now this one on the right is unstable. And that's because if I take that pendulum and I perturb it a little bit, suppose I just open a window and the air moves around a little bit in the room and the pendulum shifted to be slightly off center, it's not going to hang out here and it's certainly not going to correct itself and return back to being straight up. Instead, it's going to start swinging wildly away from the equilibrium solution it was in. On the other hand, if I take this pendulum hanging straight down and I perturb it a little bit, now there are two possibilities. If the pendulum has no friction, then it would actually just kind of go back and forth forever. That's actually not technically what I want to think of as stable, but if you imagine that it has some friction, like the hinge up here is a little bit rusty, then it's going to start swinging a little bit, but then over time you would see it sort of drop off and return towards the stable equilibrium that it was originally in. So this is going to be our working idea of a stable equilibrium versus an unstable equilibrium. For stability, you imagine that a little perturbation isn't going to wildly affect the system. A little perturbation would eventually correct itself, essentially returning to the state it was in. With an unstable equilibrium, a little perturbation can cause a giant change in behavior. So if I slightly move this pendulum, it's not going to correct itself. It's going to swing far away. Let's take that train of thought to the two models that we've been looking at recently. So the first one is our logistic model. And the other one doesn't have a great name, but it's the logistic model where we threw a negative in front of it, and that causes like a threshold below which you get extinction and above which you get explosive growth. We had phase lines for each of these, and I think the phase lines are all that we need to really conclude what we want to call that carrying capacity K for each. So if I do 0 and K, the two equilibrium solutions for both of these, then we know that a population between 0 and K for the logistic model would grow to K, but above the carrying capacity would decrease down towards K. So K is an equilibrium solution. Imagine K is 200. So 200 birds on an island is right at the carrying capacity. What happens if there's a big storm and then there are 194 birds? You come down here, you would return back to K over time. Similarly, if there's a baby boom and suddenly there are 210 birds, you would decay back down towards K. So this is a stable equilibrium. And when we're looking at these first order autonomous differential equations like we've been discussing, we would call this a sink. So solutions near K kind of sink towards K. On the other hand, for this model where we threw a negative sign on the right-hand side, what we said was that below K, you go extinct. There's just not enough members of the population to create, a successful population. But above K, you would experience rapid growth. In that model, we identified K as an equilibrium solution, but we said it was almost kind of artificial because why would you be right at K if you're going to have explosive growth right above K? So it's kind of a threshold between two zones. And what we can now say is that if you are right at K, let's say K is 200, and then suddenly there's a big storm and there are 194 birds left, according to this model, they're actually going to go extinct. So we would go from 200 to extinct. Similarly, if we're right at 200 and there's a baby boom and suddenly we have more than 200, according to this model, we should have explosive growth. So neither scenario is going to drive us back towards K. In fact, we're going to leave K quite dramatically, both to the left and right. So this would be an unstable equilibrium. And for this type of first order equation, we would call this a source. Solutions are kind of emanating away from K. Now you might be wondering if everything would fit into this box, and the answer is no. I'll just draw it up in the top right corner. If you have something like an equilibrium solution, and you have perhaps growth to the left and to the right, that's not a sink or a source. We just call this kind of other catch-all phrase a node. Similarly, you could have decay to the left and right. Again, that wouldn't be a sink or a source, that would just be a node. So we have sinks, sources, and nodes. Nodes are just kind of like everything else. Now we can do that out loud analysis whenever we have an equilibrium solution, but it's nice to have a concrete mathematical way of testing whether or not an equilibrium solution might be a sink or source. So we do that with this process called linearization, which is really just a fancy way of saying we're going to take the right-hand side of our autonomous first-order differential equations. So here this right-hand side indicates that we have an autonomous system. Okay. So if we have a differential equation, dy dt equals f of y, that's just the right-hand side of our differential equation, and we assume it's autonomous, it only depends on y. Then if we found an equilibrium point y naught, what we want to do is differentiate the right-hand side. So we'll compute f prime, plug in y naught, and the sign can tell you if y naught is a sink or a source. If f prime at y naught is less than 0, it's negative, then y naught is a sink. In other words, we have stability. If the derivative at our equilibrium solution is positive, then it's a source, and we have an unstable equilibrium. And as is often the case when you have tests with derivatives, there's an inconclusive possibility. So if f prime at y naught is 0, then the test has failed, and we just need a little bit more information. Let's practice this test on this differential equation, dy dt equals y. You might recognize that that's actually exponential growth. If it was dp dt equals p, or even dp dt equals rp with r equal to 1, this is exponential growth. The equilibrium solution is going to be a value of y that makes dy dt always equal to 0. And there's only one at y equals 0. So that's the first thing we need to do is find any equilibrium solutions. Next, let's identify what the right-hand side function is. That's f of y equals y. So if we compute its derivative at y naught, the derivative is actually always 1. So if I plug in y naught, it's still 1. Since 1 is positive, that tells us that 0 is a source. And that should agree with the phase line, because if I sketch the phase line, it's a pretty simple differential equation, especially without any interesting value for r. So we have an equilibrium solution at y equals 0. And then to the right, y is positive, so dy dt is positive. To the left, y is negative, so dy dt is negative. And we can see that regardless of what y is modeling, whether it's a population or something that could go negative, if you're at 0 and then you get slightly moved away from 0, you're going to really leave 0. So this is an unstable equilibrium. Okay, here are a few other examples. Let me do the first one, and then you can pause and work through examples 4 and 5 on your own, and then we'll come back together and you can check your answers with me. Okay, so for this first one, the equilibrium solutions are at 0 and 2. You can read those off just because this is written in nice factored form. To take the derivative, I think I would rather expand that right-hand side and write this as 2y minus y squared. So then f prime of y is the derivative of that, so that's 2 minus 2y. So then if I plug in 0, we get f prime at 0 is 2. That's positive, so that tells us it's a source. Whereas f prime at 2 is 2 minus 4, that's negative 2 actually. That's less than 0, and that's a sink. As is always the case when you have signs test, you don't really care that it's 2 and negative 2. If you can just tell it's positive or negative in a faster way than actually computing up that number, that's all you really need. But here we have a source and a sink. And just for good measure, let's draw the phase line and make sure that it agrees. So let's see if I put my phase line up here and we'll just sketch the big picture behavior of this differential equation. We've got two equilibria, one at 0 and one at 2. And let's see, if I'm to the left of 0, then I have negative, positive, that's going to be negative. If I'm at, say, 1, then we have positive, positive, so that's positive. And then if I'm at 1,000,000, we have positive, negative, so that is negative, and that does agree with what we said. So 0 is an unstable equilibrium, it's a source, and 2 is a stable equilibrium, it's a sink. This is actually really like the logistic model. So this form of this differential equation, you can recognize that that's actually equivalent to having a logistic differential equation. Okay, go ahead and pause this video to do examples 4 and 5. All right, so for example 4, I'll just work through this. We have equilibria at the roots of the right-hand side. That's going to be 0, 2, and 5. And then again, I'm going to have to factor that, or not factor, but expand it out. So we'll have 10y minus 2y minus 5y is minus 7y minus 7y squared, and then plus y cubed. It's a cubic polynomial. So then the derivative is going to be f prime of y equals 10 minus 14y plus 3y squared. So if we plug in those equilibrium solutions, we'll get f prime at 0 is 10. That's greater than 0, so that's a source. Okay, then for f prime of 2, I think it's probably going to be a sink just based on the fact that this is a quadratic and this is a cubic. But if we plug in 2, we get 10 minus 28 plus 12. So that's 22 minus 28. That is going to be negative 6. So that tells us a sink. And again, if you can tell what the sign is, that's the most important thing. And then lastly, f prime at 5, I think will probably be a source. But if you do 10 minus 70 plus 75, so you get 15. I just plug that in my calculator, but that's greater than 0, so that's a source. You can actually sketch the phase line based on that information and then check that that matches your expectations for the differential equation. Because this is a pretty simple differential equation, so we get 0 2, 5. And based on our information, we think that it should go right and left. Sorry, I said that kind of backwards, but to the left of 0, it should go to the left. To the right of 0, it should go to the right. That's because 0 is a source. 2, on the other hand, is a sink. So we should see that kind of behavior. To the left of 2, it moves to the right. To the right of 2, it moves to the left. And then 5 is a source, so we get a similar behavior around 5 compared with 0. I didn't leave very much room for myself to do number 5, but let's just say the equilibria are at 0 and 2. And if you expand out that polynomial, right-hand side, you get 2y squared minus y cubed. And you get f prime at 0 is 0. So 0 is inconclusive. And f prime at 2 is 4, so that's positive. 2 is a source. Okay, let's sketch a phase line, see what's happening at 0. Okay, to the left of 0, we have a negative number squared, so that's positive. 2 minus a negative number is positive. So to the left of 0, we grow towards the right. But if I put in 1 between 0 and 2, we get 1 times 1 is also positive. And then to the right of 2, we get positive times negative. So as expected from our test, to the right of 2, we decay towards 2. So you can see that the test was inconclusive around 0 because 0 is neither sink nor a source, it's a node. If you were at 0 and you got bumped a little bit to the left, you would go back to 0. But if you got bumped a little bit to the right, you would completely leave 0 and go to 2. So that's one way that the test can fail, is because you're detecting one of these other types of situations, which is neither a sink nor a source. Okay, let's use some of these calculus ideas to create our own model, which is going to be a model for a population that satisfies the following conditions. 0 is an equilibrium. Typically, you want that because you want your model to reflect the fact that if your fish tank is empty and it's a closed population, your fish tank will stay empty. So you should usually have that in a population model, especially a closed population model. Then we want to say that 20 is like some minimum viable population threshold. So if the population, the starting population, say is between 0 and 20, it's going to go extinct. But if it's greater than 20, it will not go extinct, it will grow. However, in this case, 100 is going to be a carrying capacity. So greater than 20 will grow, but not beyond 100. 100 is a cap. That also implies that if we're above 100, we should decay back towards 100 because that's going to be a carrying capacity like for the logistic model. Okay, let's sketch a phase line illustrating this behavior. So really, there are 3 total equilibria that I can detect from these conditions. 1 at 0, 1 at 20, it's like that minimum threshold, and 1 at 100. I don't care what happens to the left of 0 because our population is not going to go negative, but if we're between 0 and 20, we want to go extinct. So our population should travel to the left between 0 and 20. Between 20 and 100, it should grow. But then greater than 100, it should go back down towards 100 because you've exceeded your carrying capacity at that point. For symmetry, it might make sense to go ahead and fill in a behavior to the left of 0, which is traveling to the right. You could also travel to the left, but I think that this alternating signs is the easiest thing to capture with a polynomial. So what we want to have is a right-hand side of our differential equation with these 3 equilibria. And if I were to sketch that function, I would know that its derivative at 0 should be negative because that's going to be a sink. its derivative at 20 should be positive because that's a source, and its derivative at 100 should be negative because that's another sink. So you can kind of sketch the right-hand side. It's going to be like negative, positive, negative. So we really just want a right-hand side, which is kind of like this cubic. So that's the shape of f of p if we're setting up a differential equation of the form dp dt equals f of p. Okay, so I'm going to say dp dt is going to be like a cubic polynomial with roots p 20, so it's got a factor of p minus 20, and 100, so p minus 100. So that captures the equilibrium solutions. As it's written, though, at this stage, if I were to multiply this out, it would be a cubic with positive leading coefficient. That would grow towards infinity. So let's do negative. And then to give us a little control over the population to throw in a parameter, let's do negative r, where here r is going to be greater than 0. Okay, so this equation captures the described behavior. We're at the end of this lesson, but I just want to call back to an earlier idea. If this is a closed population model, what is beta minus mu? Well, for a closed population model, dp dt is beta minus mu times p. So if I took away, say, that first copy of p, then beta minus mu is everything else. So that would be negative r times p minus 20 times p minus 100. Okay, that was just a little return to an earlier lesson. I hope you enjoyed this look at sinks and sources and nodes. Thank you for your attention.